So at the heart of this problem is really the work energy theorem. And let's go through that. So the work energy theorem, if you've looked at that, if you haven't watched videos or read about the work energy theorem, which you'll know if you don't know the name of it, points out that the net work, so after all the positive and negative works have been accounted for, so if there is a net amount of work left, it will show up as a change in the object's kinetic energy. And that's the work energy theorem. And it is certainly appropriate here, and here's a few things that lead me to think that. First of all, the word distance, that, in physics, as soon as I see that, I know in kinematics we worked at distances a lot, but really the first thing I think about when I see distance is work, because it's almost always easier than finding it any other way. The other thing that I look at here is they've all got kinetic energy, and they're all going to stop and lose the kinetic energy. So they have an initial kinetic energy, and they have, after they stop, they'll have a final kinetic energy. And that is at the very heart of change in. Anytime you have change in, you have the final state or amount, so the kinetic energy final in this case, minus the original. That is what, we use sub-zero there. So that is what change in means. And then net work would be whatever the net force is on that object times the distance stopped. Well, in this case stopped, but the distance it's applied. So really, I kind of would like to, if you're struggling with this one, I almost feel like I should leave it here now that I've kind of pointed you in that direction. Well, let me put it to you this way. In a minute, I'm going to continue through. If I were you and I was like, how should I even start this? Right? Well, you didn't approach it this way. Just pause the video, go off, see what you get, and come back. You don't have to watch it all, just because you started. It doesn't mean you have to finish all the way through. I'll be here. Don't worry. I'm not going anywhere. So I'll give you a second. Okay. So for those of you that stuck around and tried it this way, I want to see if you got it right and had the right idea. Basically then, what this problem is going to boil down to is, since they all have the same final kinetic energy. They all have the same final kinetic energy. Do you agree with me on that one? Why do you agree with me? Because they all come to a stop, right? So they all are moving and end up stopping after hitting this barrier. So their final kinetic energy for all of them is 0. Now they certainly have, potentially here, looking at it, they have different masses, different velocities, so there's going to be a variation here in initial kinetic energy. Now, let's read the problem carefully. All of the cars are going to be stopped, this is the sentence I want to focus on, are going to be stopped by the same constant force by the barrier. So the net force in this case, we're assuming the barrier is the net force, of course. Then the force is the same for everybody. And if that's the same, and of course the final is the same, then this distance is solely dependent on whoever has the most kinetic energy to start. Whoever's got the most kinetic energy is going to have, in the beginning, is going to take the longest distance to stop. And so we have to basically go through and for each of these, get a kinetic energy. And so, of course, and I'll start you off, but I think after that I'll leave you. So I'm going to go 1/2 for letter A, 1,000 times v squared, which is 6, that's 36. And then for B, I've got 1/2 of 1,600 times 8 squared is 64. And for C, I have 1/2 of 1,200 times, extra parenthesis there, times 64. And for D, I have 1/2 of 1,600 times 16. And so, real quickly, looking at this, I have for A, looking like 500 times 36. I'm going to be lazy on that one. Oh, wait, I got to calculator sitting right in front of me here in the room, so we'll just do it that way. So 500 times 36, I can do this. 18,000 joules, of course. B is going to be 800 times 64. That's 51,200 joules. C is going to be 600 times 64. That's 38,400. And D is 800 times 16. 12,800. Now, here's joules. Here's the thing. Somebody that doesn't quite grasp everything about this problem is going to look at it, see velocity, see mass, find the kinetic energies, and could very well be like, well, I guess I'll just go with the one with the biggest kinetic energy. And they would be right. But they wouldn't understand all the implications of what's going on here. Because there's a lot more to it than that. Yes, it turns out that the kinetic energy is the correct approach here, but this is why. And understanding that the net force on them is the same and that the work done, the net work done on each of them, is going to be equal to their change in kinetic energy and how that affects things and how they all have the same final and so forth and so on. So getting the answer to this one is one thing. Understanding what it's talking about is an entire other thing, so to speak. But I don't think I need to write the letters in order. Yeah, you can put things in order, so you're probably good from there.